Hello, everybody. So I've made summary videos before for some topics in some of the classes. I haven't done a summary for every topic in every class I teach yet, but I've made them before, and I thought this particular topic deserved a summary video more than the others, okay? So I provide the summary just so that you don't get too lost in the details of any particular problem, all right? So in this video, I'm not going to worry about the math so much. I'm going to try to explain what all the words mean and what the symbols are, and we won't get lost in details of algebra or trigonometry or anything like that, okay? All right, so here goes. So first thing on the list is a function. If I write y equals f of x, y is a function of x. And what that means is that if I know x, then I can uniquely calculate y by whatever that function is, where that function is probably going to be some kind of mathematical formula, all right? You could say that you put the x in and you get the y back out. That's what a function does. You know the x, you get the y. X, I guess the correct name for that is the independent variable. I often call it the input variable. I don't know that anybody else does that, but it seems like the right term to tell people to describe what it does. And Y, I guess the proper term for that is dependent variable, but I usually call it the output variable because it seems like a good name for it. So that's what a function is. If you know the value of one variable, you can find the value of the other, x and y, right? The variables could be different though. We don't always use x and y. Sometimes we use a letter that's a little bit more descriptive to what the variable is, like t for time or something like that. All right, so that's what a function is. Second thing on the list, the average rate of change. So we write that with the symbol delta y over delta x. And you would say that that's the average rate of change of y with respect to x. I mentioned in another video, I don't remember where, but I said, why do we say with respect to? Well, if x and y are linked together by a function, okay, x determines what y is, then any change in x is going to cause change in y, and they're changing together. It's not like the y changes all by itself independently of the x or vice versa. Change in x causes change in y, so we can say that y is changing with respect to x. All right. What's the purpose of it? It will measure how change in x causes change in y, right? Or how x and y change together. So when we find the average rate of change, we're not just trying to figure out how much y changes or how much x changes, but how they change together, all right? Quick hint, when it comes down to needing to calculate this, you can't work that out and tell me what it is unless a given value of x is provided and also delta x. Okay, you have to know x and delta x to figure out what the average rate of change is. All right, next thing. So the average rate of change leads us into the derivative. Okay, so there's our symbol for it. That's called Leibniz notation, but I'll tell you a little bit about that later. So dy over dx, the derivative. You could also call it the instantaneous rate of change of y with respect to x. When we say that, though, we usually leave out the word instantaneous, and it's often just called the rate of change, all right? But, okay, that's the symbol. This is what it's called. The purpose, well, it's like the average rate of change. It tells you how y and x are changing together, but it's more accurate. I'll say a little bit about that in a minute, okay? It's more accurate, but I guess you could say that the derivative is approximately equal to the average rate of change if delta x is very small, okay? All right, so why is the derivative like the average rate of change, but it's more accurate? Well, because there's lots of ways I can explain it. No matter how I explain it, somebody's not going to like it. But here's what I was inclined to tell you tonight. Suppose I drive 120 miles in 2 hours, okay? So I keep track of my time and I keep track of my distance as I travel. Then you could say that my average speed was 120 miles in 2 hours, and that reduces to the number 60 in units miles per hour. That's just an average. Notice that that's not real accurate. I mean, this number can't really tell me much truth about the situation. I mean, there's just too much that can happen in 2 hours. In 2 hours, like probably I speed up and slow down, maybe come to a stop. And so to say I was going 60 miles an hour is not all that descriptive by a moment to moment basis. What's the root of the word instantaneous? Instant, a moment, an instant. So the average is not that descriptive about what's happening second by second, moment by moment, and so on. Okay. The derivative, now in this situation, I'm not giving you a formula or a function, and so you can't calculate the derivative. But the derivative would tell me the speed at any instant if I could find it. All right. But given that this is just a summary video and I'm explaining the definitions and concepts, then I won't say anything else about it. But the average is not so accurate compared to the derivative. Okay. And I use movement and speed as an example. You could make the average rate of change more accurate if that, I guess the problem is this delta t right here, that change in time. It's just too big. 2 hours, like there's too much that can happen. If that delta t was smaller, I think I'd get a more accurate picture about my speed at any particular moment, right? So that's like this up here. The derivative is approximately equal to the average rate of change if delta x is very small. In this case, if delta t was significantly smaller than that, maybe on the order of fractions of a second, then this would be a little more accurate about what's happening at any instant. Okay. All right. I was running out of room, so I tried to squeeze this in here. So a hint for the derivative. All right. If you want to find the derivative, you calculate the derivative, you must have this function y is equal to a function of x. You can't calculate dy over dx if y is not a function of x. So you need to start with that and go from there. Okay? So this variable y up there, whatever that is, has to be a function of this one down here, x, in order to calculate the derivative. Just in terms of general procedures, all right? So now for some facts, all right? So as I've mentioned, delta y over delta x is approximately equal to dy over dx. The average is roughly equal to the instantaneous rate of change if delta x is very small. But the average rate of change is perfectly and exactly equal to the derivative if that original function is linear, meaning if you drew the graph of y equals f of x and it was a line, if x, the variable, has the first power, then, all right, the average is equal to the derivative. It's equal to the instantaneous rate of change. And if we ever say that some rate of change was constant, like if say that there was no formula given or anything, but it was just said verbally in some question that you're doing or some situation that you're trying to understand, the change of y with respect to x is constant and it's some number k, then that number k is going to be dy over dx. That number k is going to be the derivative. The key word there is it's got to be constant. Okay, so if you ever read something that says such and such is changing at a constant rate of whatever, well, that number, that's your derivative. Okay, nothing further to explore about it. All right, we'll continue with the summary. So there are, as there are with most things in math, there are several different notations for the derivative. For the derivative, we could say y prime, we could say f prime x, and we could say dy dx or dy over dx. Okay, they all mean the same thing. They're all indicating the derivative. Okay, and it doesn't matter which notation we use. How do you think you find the derivative? You use rules. So no matter when you're watching this, I posted the videos so that you learn the rules before you ever see any of this. So by the time we're learning about this, you know what the rules are, okay? It doesn't matter what you call the derivative. The rules are going to be the same. So if that's true, why do we write dy over dx? Why not just y prime? I have to tell you, in my experience, people don't like the dy over dx. They don't write that voluntarily. maybe because it's a fraction and they just think it's making things more complicated. The reason that we use that is because we're thinking that the derivative tells me the change in y over the change in x together, right, instantaneously, where I lose that information if I write these. You might be aware that it's still there, but it's not explicitly written in the notation. So when I see this, I think, okay, what that's telling me is how y and x change together. That's what it's telling me. This is roughly equal to the average rate of change, and I understand what that is, if delta x is small. So it gives me a way to understand the derivative, okay? All right, so you'll see Leibniz notation all over the place. Yes, so dy over dx, when we write derivatives that way, that's known as Leibniz notation. Gottfried Wilhelm von Leibniz, mathematician, philosopher, somebody that would probably be highly insulted by this portrait if he hadn't died so long ago. Yes, he was a mathematician, and his notation is named after him, okay? Anyway, so let's see. Next thing, this symbol, dy over dx when x is k. So this is asking us to evaluate the derivative at some given value of x. Again, this is just notation, all right? Well, how do we do that? Well, step one, we'll calculate the derivative with whatever rule would apply to it. And once we've got that formula, we just plug the k in for the x, all right? It's not that big of a deal. All right, let's see. That's everything. Those are all the concepts. Those are all the definitions and so on. I really cannot think of anything else summary-wise to tell you. But I thought, okay, I'm going to say all that and make the video. I might as well give an example too, all right? So take this example, all right, where it's going to have all the elements of what I was telling you about. So there's a triangle. This side is fixed. This side is variable, meaning it can take different values, and so is this angle. And as that side, if it were to get bigger or smaller, that angle would have to change also. Imagine if you're going to keep this side fixed, if you were to change either theta or x, the other one of them would have to change too to keep that side fixed, all right? So there's a triangle. We have an equation. The equation gives us, what was the very first thing on the list in my summary video? It was a function, okay? What kind of function is this? It puts x to be a function of theta. In that equation, if you knew the angle theta, this formula here would calculate the value of x, this base side of that triangle. It's a function. You know one thing, you can figure out another. That's what a function does. Now, for the sake of example, suppose I show you an average versus an instantaneous rate of change. Say I ask you to calculate delta x over delta theta if theta is 40 and it changes by a degree. Okay, this would be done that way. Theta being 41 degrees versus 40. There's delta x over delta theta, all according to that function. Literally, that's the change in x over the change in the angle. If the angle changes from 40 to what? 41 degrees, okay? If you use your calculator and figure out this number, it turns out to be about negative 0.207 feet per degree. Why feet per degree? Well, that number, x, that's the side of a triangle, it's in feet. And theta, the angle, as I was plugging it in, was in degrees, all right? So it's negative 0.207 feet per degree. All right, so that's an example of an average rate of change. I had to know this function to start with, and I had to know some initial value of theta, that variable down there, and I had to know how much was changing. But between those three things, I could calculate the average rate of change. What about the instantaneous rate of change? Well, we said that was the derivative, right? So let's see. We look back at the function, okay? X is 5 over tangent theta. What's the derivative of that? Well, how about this? Let's write this as x is 5 times cotangent theta. That's the same thing, right? 1 over tangent, that's cotangent. So I could write it as 5 times 1 over tangent, so 5 times cotangent. Now, if I'm going to find the derivative of this, right? This function, x being a function of theta, that's what dx over d theta is. Look for the function where x is a function of theta and use the rules to find the derivative of that function. Well, it's right here. It's 5 cotangent theta. The derivative of cotangent is negative cosecant squared. So there's your derivative. Suppose I ask you to evaluate the derivative when theta is 40 so that I can compare with this. Okay, see that one we already did? Then I would do like so. Cosecant is 1 over sine. Okay, so it's negative 5 over sine of 40 degrees all squared. And then you'll get this number right out of the calculator. What are the units there? Well, x units, that's a distance, a length of a triangle. It's in feet over angle distance. But with trig functions, the default that you get out of the derivative is in radians. All right, so that number, negative 12.101, is feet per radian. Now, I would expect that not be feet per degree. Why? Well, because isn't the derivative supposed to be approximately equal to the average rate of change if that delta down there is small? I would say, well, 1 degree, that's pretty small. I mean, what's small? I mean, you can't, if you had a number line, there isn't a mark on it and it says small. So what's small is anybody's opinion, but I would say 1 degree is fairly small. So I would expect these to be more equal to each other, right? That was one principle that I kept bringing back up in the lesson is, yes, the derivative is approximately equal to the average rate of change if delta x is very small. This gives you a way to understand what the derivative is because you can measure the changes of the variables on your own, okay? So anyway, all right, so that's not feet per degrees, it's feet per radian, because that's going to be the default out of the derivative of a trig function, all right? But say that I'd like to prove my comparison and I want to convert to these units. So feet per radian, I need to convert that to feet per degree. So how do I do that? Well, it's known that there is a conversion factor between radians and degrees. They measure an angle, they measure the same thing. There must be a way to convert. 1 radian is 180 over pi degrees. That makes a radian about 57 degrees. If you divide 180 by pi, it's about 57. What is a radian angle? It's a 57 degree angle, okay? So by that conversion factor, I can convert this number, which is in feet per radian, to that one, which is in feet per degree. What is it? Negative 0.211 feet per degree. Same thing. No, not exactly the same, all right, but close, right? They're approximately equal to each other, all right? Okay, what's it all mean? Well, okay, so the derivative is approximately equal to the average. What's the average saying? Well, it says if the angle gets bigger by a degree, then x, the base of the triangle, has to get smaller by 0.2 feet. Does that make sense? Does it make sense that if the angle got bigger, but this side stayed the same, that x would have to get smaller? All right, so just think about it like that for a second. Because if a derivative is negative, it means, in both the derivative and the average rate of change are negative, it means that these variables are changing in opposite directions. If the derivative or the average rate of change is ever negative, it means if theta gets bigger, x gets smaller. If x gets bigger, theta gets smaller, and so on. Okay? All right. So anyway, that's why it's negative. It is true that if theta got bigger, x would have to get smaller. Okay? All right. As a way to visualize that, I'll include this in the summary because in my videos, I did sometimes draw some diagrams to get you to understand why the derivative was the size that it was or had a positive or negative sign. So do you have the imagination to see why that's negative? Is it true that if you held that constant right there and theta got bigger, x would have to get smaller? Well, think of it like this, if you're having trouble seeing that. Here's just a triangle. We'll say that's 5 feet, okay? And look at theta and x. There they are, all right? How would you have to change this triangle to make the angle bigger? Wouldn't you have to push this in that way? Oh, like this. So that's still 5, 5 and 5. theta's bigger here, but if theta gets larger, the x has to get smaller. You have to push that corner in this way to make the angle bigger. Okay, so that's why the derivative was negative. These two things are changing in opposite direction. If one gets bigger, that means the other gets smaller. So I can see that in the sign of my derivative, and I can even see it in the picture, okay? What about the number? I told you what the sign means. What about the number? Well, it means that if the angle gets 1 degree bigger from 40, that side of the triangle will shrink by about 0.2 feet. That's what both of these say, all right? So yes, if I push this that way so that that angle gets 1 degree bigger, this side here shrinks by 0.2 feet. All right. So there is that. And then I remember one thing I forgot to mention is that delta x can be negative. I realized when I was making this video or preparing the slides, I never included an example where delta x can be negative. It can, all right? It's just how much x changes by. That's what literally delta x means. So real quick, just so that I can have a clear conscience that I've done that, take this function, y is 1 over x, calculate the average rate of change if x is 4 and delta x is negative 0.1. So if x is initially 4 and it changes by negative 0.1, that just means it's getting smaller. It's going from 4 to 3.9. Okay, so yes, delta x would be negative. It would look like that. Y would be like this. So look at it. If x gets smaller, what's y do? Y gets bigger. X gets smaller, y gets bigger. Derivative in delta, average rate of change is negative. Okay, remember in the last example I said if the variables move different directions, the derivative or the average rate of change will be negative. There it is. Okay, yeah, that's smaller and that's bigger. There's the math and the number. All right, so that's the summary. I thought I'd say one more thing, that just because this is relevant to me and something that happened to me recently, I was looking through, I still like to learn, I like to read, and I'm always trying to learn something new in math, and I'll never learn everything, of course. And just the other day, I'd never learned much about fluid mechanics. I just never had the interest in it and never took the time to do it. And so the other day, though, I thought I'm going to learn something about this. I should know about it, so I'm going to spend the time and learn everything I can. And, just then, like, I encountered this derivative right here. There's an average rate of change with delta A going to 0. Well, that's your derivative. If delta A would just be very small, then this would be an approximation. But there, I ran into it just then. And here, trying to explain a fundamental concept of fluid mechanics, that pressure increases with depth in a certain specific way. Then here's a diagram meant to explain this reasoning to develop this principle that's at the bottom of the page. But look at it. There's the Leibniz notation, dp over dy, change in pressure with elevation. So there, I have a way to look at that and think about what that's telling me. That's a derivative, but it's trying to capture the change in the pressure with respect to the depth. If you look at that diagram, y is the depth, okay? And it's explained elsewhere that P is the pressure. So, all right, there. I mean, just even in that, I see some things on our quiz. I see other things too. And of course, we're not learning everything at once, but just the other day, just as I was about to cover this topic, I was learning about something else that just happened to involve it quite a bit.